This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Good morning and welcome to the fifth lecture of the Introduction to General Relativity. Today we talk about tangent spaces. Now, under this rather unassuming name goes really a lot of the basic concept mathematically that underlie general relativity. So this is a really important lecture. And there is a lead question. The lead question is the following. On a manifold, if you consider a curve, what is the velocity of that curve at the point P? Now this is velocity and not speed. And later on we will meet speed, but speed cannot be defined before a so-called metric is defined on a manifold. That will come later. We'll start with velocity. And it is tradition to call the velocity a vector, and in fact it will be a vector in our formalism. But I ask you at first to completely erase anything you ever learned about velocities. We're trying to rediscover it. So what is the velocity of a curve gamma at a point P? And rather than making many motivating introductory remarks that are going to confuse you further, we immediately start with the definition and then we discuss the definition. So first is velocities. The definition is as follows. We consider a smooth manifold, MOA. That's a topological manifold with a smooth atlas. And we consider a curve on that manifold, a curve gamma, from R into the manifold that is at least C1. So it can be once continuously differentiated with respect to the charts of this smooth atlas. And we suppose that the curve gamma at some parameter value lambda 0 hits this point P, because otherwise it's meaningless to ask what the velocity of the curve at the point P is. Now there's the following definition. The velocity of gamma at P is, and now it comes, the linear map. So this is something you need to get used to, that velocities in vectors in general, but we start with velocities, are linear maps. It's the linear map that we call curly V, like velocity, of the curve gamma in the point P. The velocity of the curve gamma in the point P, what mathematical object is it? It's a linear map. A linear map needs to go from one vector space to another vector space. The vector space we start from, and which I will explain in a second, is the vector space C infinity M, or inspiring name, very simple object, linear map into the real numbers, which are an R vector space if you equip them with their own addition and multiplication. Now this guy, what is it? This is the guy, very simply, of all smooth functions on the manifold. So if f is a smooth function, then C infinity M as a set is the collection of these smooth functions equipped with, we need addition and S multiplication, and that is just pointwise. So two of those are added, so I declare the addition to be a smooth map again, defined at a point P of the manifold as f of P plus g of P, where this plus is now the plus in the real numbers where these functions take their values, and similarly lambda g of P defined as lambda times in the real numbers g of P. And the set with these two operations is a vector space. It's the vector space of smooth functions, so it makes sense to talk about a linear map from here to here. And the velocity is a linear map that eats arbitrary function, any function, and spits out a real number according to the following rule. It takes this function and it maps it to V gamma P of f. Now I need to tell you how this is defined. This is f after gamma. You take the derivative of that and you evaluate at the parameter value lambda 0. That's it. That is the velocity of gamma at a point P. Now, an intuition for this is very helpful. And in fact, if you find this surprising as a definition for velocity, this is exactly what children, uncorrupted by high school physics, capture as the concept of velocity. Because it's the following. You run around through the world as a child and you observe the world around you. So say that in the world around you there is some temperature function, f, but you must be able to do it for any f, right? But if you see some temperature function whose level lines I drew here, you run through the world and you see, as you run around as a child, you look at the temperature wherever you are. So you have the situation that you run around, which is this, and there is a temperature around, and you feel the temperature wherever you are. So this is just a function from R to R, time, temperature, okay? And you observe how the temperature changes, the rate of change of temperature as you run along, okay? So what this gives you the directional derivative of f as you run along the curve gamma if you're at the point P. You feel how that changes. So the velocity of a curve at the point P is the directional derivative. And in the past, so this is really just in order to make contact, in the past you might have talked about the velocity, and now I'm talking in charts. I'm going to make this precise. I should only write this like this. You might have thought about the directional derivative more like this. You take the gradient of f, you dot it into the, what you would say, yes, that's a vector, right? You would have dotted it into there, and that's the directional derivative. Now, of course, you can consider this, but this is only really very roughly. You could, of course, say, no, vi del I is the differential operator that acts on f. And the only shift in philosophy is that rather than saying this is the vector or the components of the vector, in differential geometry you say this is the vector. It's a linear map that takes an f and maps it to a number because you evaluate at a point. So you rather pull this derivative to there, right? So one could say in programmatic brevity, we want to understand vectors, or vectors in differential geometry survive as the directional derivatives they induce. But if you know how this acts on any function, you can make it act on the coordinate functions, and then you get deltas, and then you can recover all the components. So really, if you know the directional derivative, how it acts on just any function, you can fully recover the components. Okay? This is a very simple shift of now you could say this is the basis for these components. Okay, so now delete everything I said, because everything I said will now be made precise where exactly it takes place. Okay? But so there is nothing fantastic happening, it's just a very slight shift of perspective, which is extremely powerful and leads to the whole idea of tangent spaces in differential geometry. Okay, so this is actually a very intuitive concept. We're coming back to that. Now immediately we come to tangent spaces, or the tangent vector space, because that is what it's going to be. The definition is as follows. Definition: for each point P of the manifold, we define the set. So first of all, a set T sub Pm, called the tangent space 2M at the point P, TPM, and this is simply the collection of all possible tangent vectors to all possible smooth curves through the point. Okay? So the picture for this set is you have a point, and you look at all the curves through that point, and that curve will have a tangent vector here. You could say a directional derivative associated with it. And this curve has one, and that curve has one. Well, there will be a curve exactly like the other one going through the same point, but at double parameter speed. That will give you a different directional derivative because it scales. We'll see all this. There could be through a point one curve that's different from another one, but nevertheless they give the same tangent vector and so on. It's very intuitive. So this is almost a picture. You just have to think at the tangent vectors or the velocities at this point as being associated to this curve. Now, do you see we defined the tangent space as these velocities, as these maps? None of these constructions made any reference to an ambient space around it. So although for intuitive purposes you might think of the TPM in a fashion I alluded to last time, a little like this would make reference to an ambient space, but this is actually the cleverer notion. Now, in the beginning of differential geometry, there was a debate for many years. Is it better to define objects intrinsically, only lying within the manifold, or is it better to take the manifold, embed it in a bigger space, and then take this extrinsic point of view, and does it lead to the same results? And famous embedding theorems at all structural levels say it doesn't matter. You always find a big enough ambient space to embed it and to understand it in this way. Okay, so this debate is settled. Now the question is, why do we take this perspective rather than this one? Well, if this is finally going to be the universe, all of the universe, space-time, it would be a little bit uneconomical to refer to something around the universe, right? So it's better to talk from within the universe to define all the concepts. That's somehow a clever choice. So we prefer this, and also technically it points to the right ideas. Okay, so rather this than this. Rather this than this as a picture, although really everybody thinks of it like this as well. Okay, but technically you must not. So that's the definition of the tangent space, and well, that is just a set. Now the question is, do the velocities at a point form a vector space? Well, that is true, they do. So observation, and it's a key observation. TPM can be made into a vector space. And because this is so important, and this is a technical key point that you're going to use all the time, I'll show this in detail. And already in this calculation, you learn all the techniques that you need in the future for your own calculations. So it's not just a proof that you then never look at again, it's an important construction. So what do we need to do? We define an addition and an S multiplication, and that's very easy because the elements of here are linear maps with values in R. Well, so you can immediately add them. So you can immediately take an element of TPM and an element of the same TPM. So you cannot take a vector here and a vector here and add them. That's not possible. But you can take two vectors at the same point, and you can immediately add them. So you get V gamma P plus V delta P. It's the vector because all the elements are velocities to some curve. Two different elements will be defined with respect to different underlying curves, right? You can immediately define this because you know this is such a linear map, so you can apply it to an arbitrary smooth function, and you define the sum as gamma P acting on F plus gamma V delta P acting on the same F, And this is just the addition in the real numbers, whereas this defines the addition in TPM. Okay? You can immediately add because of the structure of these objects, and then you have an S multiplication, R cross TP, and that works like lambda S multiplication V of some gamma P, defined by action on F, exactly the same with the real numbers V gamma P acting on F. Now, I can add them all right, but there's one problem. If I add two maps, what I get out is a map of that type, and a map of that type is a map from C infinity M to R, a real map. So it's a map from C infinity M to R. I could have also written C infinity M star. And here the same, a map from C infinity M R, because, well, that's just what you get if you add two such maps. However, in order for these to be a vector space addition and S multiplication, it is necessary that these two operations close within TPM, so that you don't just get a map of this type, but you get a map of this type that lies in C infinity M R, that lies in this specific subset. It needs to be a map that can be generated of this type, that can be generated from a curve. That is not clear. You can add and you have a map, but is it generated from this curve? So it remains to be shown. So we're always almost there. It remains to be shown that first, there exists a curve, sigma curve, such that the sum of the velocity of gamma at P plus the velocity of delta at P, that there exists a curve sigma such that the sum is not only a map of the type, but is actually the velocity of a third curve at the point, arises in the way in which the elements of this space must arise. Okay, it's important. And similarly, it must be shown that there exists a curve, I don't know how to call it, like the sigma tau curve, such that lambda times V gamma P is V tau comma P. Okay, so this we need to do. So the remaining proof focuses, or can focus on this. Let's start with this first case, right? We have this V gamma P, and we do the S multiplication we defined right here. Okay? I need to find a curve tau such that the result is the velocity of this curve tau. Okay? I construct this curve. You can say, how do you construct this? Well, by looking at it, it's easiest to just construct. So we define the curve tau as a curve R to M by sending lambda to tau of lambda, but tau of lambda is lambda is a bad choice because I chose lambda here. I need to choose a different parameter. But because I'm so used we are also used to using lambda as the parameter, let's take here an alpha as the multiplication, right? So alpha is the real number by which I multiply. Okay, so I set this to sigma, and I run through the old curve at alpha times the parameter speed, if you wish. Okay? I just do this, and it's clever to write this as sigma after mu down alpha of lambda, where the mu down alpha is a very simple thing. It takes a real number to a real number, r, to alpha times this number. Well, this is, of course, what's written here. You take the mu of lambda, this is alpha times lambda, that's this. We write it like this because we need to do the chain rule in a second. Okay, so I just claim this curve does the trick. This curve is the one that reproduces alpha times this. Well, let's calculate. since we look at what's the tangent vector to the new curve tau in the point P. And we first check that T at the same parameter value lambda 0 is sigma of alpha lambda 0. I should have, it needs to go through the same point. Well, it will. For some lambda 0, it will hit the point. But I need to, hang on a second. I need to take, so the curve sigma, not sigma, I'm sorry, the curve gamma went through the point P. Oh, now you deleted it, okay. Through the point P at parameter value lambda 0. So I take lambda minus lambda 0 at this point. Why not? And then T of 0 will be gamma of lambda 0. Now we got it. I do it like this. Then the T of 0 will be gamma of lambda 0. And then I can calculate the velocity to tau at the point P as, now by definition, it's f after tau. I take this like this, and I take the derivative at the point where we run through P. But this is here the parameter value 0. Okay, this is one way to do it. Equals, and now I need to take this derivative, and for that it's clever to write down what I wrote down here. This is, so I take this mu alpha, I have here plus lambda 0 for simplicity, is gamma after mu alpha of lambda. Okay, this is an R, this is an R, that's fine. So I now have this chain rule, is f after gamma after mu alpha, derivative at the point 0. And now, of course, you know how to do this. This is f after gamma, derivative at the point mu alpha of 0. But mu alpha of 0 is just lambda 0 times the inner derivative is the derivative of this guy with respect to r. So this is just an alpha times alpha. Oh, that's excellent, because this is alpha times the velocity to gamma in the point P, because gamma of lambda 0 is the point P. Okay, so sorry for the intermediate confusion, but here, so there exists a curve. Indeed, this curve tau reproduces this here. Okay, so that was the easy part. Now comes the almost as easy part. So that's number... please leave this for a second, for 1 second, please. Okay. So now for the sum, it works as follows. Well, we'll leave it for a moment. It works as follows. So we want to look at the velocity to gamma at a point P plus the velocity to delta at a point P. And we need to construct, we need to find a curve sigma that at the point P has the velocity that corresponds to what I defined here. So construct, in order to construct this curve, we need to do something extremely ugly. We make a choice of chart. Make a choice of chart ux that contains the point in question we're looking at. Now, the moment I say make a choice of chart, immediately your ill definition alarm bells need to ring. Say, okay, I bear with you, but please, if in the end anything depends on this chart, I'm not going to buy it. Okay? It's very important. So again, I'm not against choosing charts. I'm just against choosing charts and not knowing what a great assumption you're making here. Okay? But it turns out it's no assumption at all. Make a choice of chart and define. We define the curve sigma in the real world, R to M, as follows. Sigma of lambda is, I define now a curve in the chart, and once I have it, I take it back into the real world by x to the minus 1. Okay? And in the chart, I take the chart representative of the curve gamma, and I take it at the point lambda 0 plus lambda. Lambda 0 is the point where gamma hits P. Plus, I take the chart representative of the curve delta at the point lambda 1 plus lambda. Lambda 1 is the point where delta hits P. And I subtract a constant RD element, namely x after gamma at the point lambda 0. That doesn't depend on lambda at all, nevertheless I need it. And this is in the chart, and of course in the chart this is an element for specific lambda, this is an element in RD, and with the lambda free, it's a map from here to here. I can add this in RD, I can add this in RD in the chart. Terribly ill-defined from a general point of view. If you didn't have a chart, it wouldn't make any sense. But you do this in the chart and you go back from the chart to the real world, which doesn't make it better because you need the x and the x inverse. Right? Nevertheless, bear with me, I claim this sum, this sigma, does the trick. This sigma in the real world satisfies this up here. Now this we need to calculate. So the first thing we need to do, we need to see whether sigma at all hits this point P and at what parameter value. We need to look at sigma of 0. And maybe in order to remind ourselves of the terrible sin we committed, we indicate the sigma sub x, so we have a constant reminder this construction depends on the chart map x. Okay, so what is sigma x of 0 equals x after gamma of lambda 0 plus, I write it down, is x after gamma of lambda 0, x inverse, plus x after delta of lambda 1 minus x after gamma of lambda 0. I need this one to kill this one, and then I have just x inverse x delta, this is delta of lambda 1, is the point P. Okay, so parameter value 0, it runs through P, otherwise this makes no sense in the first place. And now the actual calculation is as follows. V of this curve sigma x that I claim to do the trick, sigma x, in the point P equals, well, let's use the definition. Acting on a function, I need to have it act on a function to calculate, is f after this sigma x prime at the parameter value where it hits P, that's 0, at 0. That's this thing. We need to calculate and we need to end up here. If we did, we found the curve. Equals. Now, I plug it in or I choose another intermediate chart. I use an intermediate chart. So f after x inverse after x after sigma x. I'm allowed to do this, right? I insert the identity, that's the standard trick, derivative at 0, and then I use the associativity of the composition to re-bracket like this. Now, this is the derivative, and now let's see what kind of objects we have. This is a function from RD to R, right? Maybe it helps to write down what happens here. The curve sigma lands here. The arbitrary function f is defined there. We have a chart here. We have f after x inverse, and here we have x after sigma. So we know that f after x inverse goes from a part of RD to R, and x after sigma x, so the guy is called sigma x, x after sigma x is this one, goes from R to RD. To RD, and between them there's a composition, there's a derivative. Fantastic, is undergraduate analysis, right? So we do the multidimensional chain rule of undergraduate analysis, and that works as follows. We take the inner derivative first. Well, you don't need to take it first, but we need to take it. So you take the derivative at the point 0, but because here this is multi-valued, you take the ith component of it. Or you can also put the ith component here and take it here, it's the same thing. And here you take the partial derivative in the ith direction, okay, of the ith entry here. This is this f after x inverse. And after you did the derivation, you evaluate at the point x after sigma x of 0, x of sigma x of 0. Sigma x of 0 is p, so that's at the point x of p. Okay, so now we're left with the task of calculating this beast where sigma x is given like this. Let's do this first. That's not so difficult. Because x, or maybe I put the I here, it's really the same thing because that's the final function, that a map that acts. It's the, no, I put it here. It's x after sigma x, that means that kills this bit. And so we have here a function from R to Rd, and its ith component. Oh, we know how to derive this. We derive this and this and this. What's the result? The derivative of the first one with respect to lambda is x after gamma prime evaluated at, at 0 is evaluated at lambda 0. Okay? Plus, then this part, because the x inverse has been killed, right? That frees us here. This is x after delta prime at lambda 0 evaluated is at lambda 1. And this is constant. This doesn't contain lambda at all, so there is nothing else to it. So this part here is this. And now you see the magic. Although we had this terrible construction where we go down to the chart, add there, terribly ill-defined. Ill-defined, it's well-defined here, but it's ill-defined under a change of chart. The derivative here at the end of the day leads you a product, a sum rule, okay? And so what you get here, you now see it, it's this factor here in front, is this guy, and that's of course distributive over this number which is in R, this multiplication which is in R. But what is this? Well, I write it down. It's x after gamma prime at lambda 0 times del I f after x inverse at p, at x of p, plus the same expression with x after delta prime at lambda 1 times del I f after x inverse at x of p. But now we do this backwards with the chain rule, multi-dimensional, and I'm sorry, I took the ith here, so I should have had an I here and here, so I have an I here and an I here, which is contracted like this. And now I do the multi-dimensional undergraduate chain rule backwards, and what I get is f after gamma, hang on a second, f after, I get f, so I get first this thing here, and then I can remove the others. This is f after gamma prime at 0 plus f after delta prime at 0, no, at lambda 0 and at lambda 1, right? These are the evaluation points here. And that's of course nothing but the velocity to gamma at p plus the velocity after I acted on f plus the velocity of delta at p after acting on f. So we compared the left-hand side with the right-hand side. We didn't make any assumption on f other than that it comes from this set. That is, we have exactly v gamma p with this addition, which is defined like this. Delta p is v sigma p. And although we intermediately chose this chart, neither the left-hand side nor the right-hand side depends on that. So in fact, this is the curve that does the trick. Yes?
I don't see where, so I didn't really get the exact point. We have to do the proof that there exists a curve sigma.
Such that the result we already defined,
is a well-defined C infinity. So we have
such that the result arises as the tangent to a curve, yes.
and then you made use in your, so I can prove the existence by just constructing one.
Yes?
And there you pointed out that it might not, there might not exist such a chart.
No. I constructed a candidate for a curve that does the trick by using a chart.
By using a chart, but
Yeah.
somewhere at this point, like what you pointed out, there might not even...
No, the chart, if I choose some chart, the point is, no, I don't need to assume the existence of a special chart. Make a choice of any chart that covers the point, and that is possible is the definition of a topological manifold. It must only be chart independent. So if I had chosen another chart, would the result change? The quick answer is no, because you would have a y everywhere, but the result would work out the same. Precisely because I didn't make any further assumptions on the chart. Thank you for the question. Yes, yes.
And you told us that it is better to think in this completely intrinsic picture. Yeah?
Yes.
But here we see without seeing that we have a manifold which can be mapped to the real space. We cannot perform this proof.
Yes.
Nevertheless, it is necessary that locally we can describe whatever it is by a linear Euclidean rule.
Okay, I wouldn't agree with the Euclidean, but the idea is right. The only thing I meant is with the picture with the tangent space. So it's the idea of a topological manifold that locally its point can be mapped in a continuous way, one-to-one, to some RD. But what I meant by this embedding picture is that you choose an R to the 1000 to look at a 5-dimensional manifold. Well, you don't need to go that high. But say in order to look at a 3-dimensional manifold, you might have to go to R7 to embed it such that what you get by the intrinsic construction, which only works with R3s, that you get it as the tangent spaces as you would define them if you were in an R7. So that's even worse. That really goes to an ambient space that lies around it, whereas the manifold definition just requires that pieces of the manifold can go to an R to the dimension of the manifold. Okay, so that's the difference. But it's exactly the point of not looking at an arbitrary topological space. Then, for an arbitrary topological space, you don't have charts in the first place. So we make a huge assumption. We say the whole universe, or whatever you look at, the whole manifold, locally it looks like RD. That's a massive assumption, and that's the assumption that space-time or space is a topological manifold. Yes?
On the first line there, the x disappeared, and I must admit that I do not see if we did the chain go forward,
Yes.
then x would...
Okay, so you want me to insert one more line. The chain rule of just this bit backwards, the other bit works the same. The chain rule of just this bit backwards is f after x inverse after x after gamma derivative at the point lambda 0. Plus, and then the same thing over here, and here it vanishes again, and then you get this and the same here. It does vanish, it goes away, very importantly. Yes?
I was confused by the proof of the first part.
Yes?
So can you explain in words why we didn't use
Yes.
the map over there?
Oh, because, yeah, okay, so okay, picture for the proofs, okay? So the first one went like this. You have the real world, M, and you have a curve in there, and I indicate equal intervals of the parameter until I arrive at this point by these lengths. So every time this curve is interrupted, the parameter has increased by 1. Now, very intuitively, really intuitively, you may think of the velocity as this little arrow. In fact, it turns out in the real world you must not think of an arrow, but in the chart you can. Nevertheless, I now do this but I want you to think of this arrow as the directional derivative in the direction of this arrow. Okay, because we know that is what a vector is. So this is a bad picture, but it's not so bad to understanding the proof. So this is what we would draw normally. Now the idea was, if you want to draw double, if you want to produce double this velocity, you just run through the curve at double parameter velocity, like this. And this is what the map mu2 did. Well, it was a mu alpha, but what the map mu2 did. And the statement was that the tangent to this first curve is 2 times the tangent to the second curve if I compose the first curve gamma, if I compose it after mu2. Before it eats the parameter, it's doubled. And then you get a curve. And for that, you don't need a chart to define it. I could have pushed it down in a chart too, but that wouldn't be economical, because here, so the multiples you get by just running through the same curve faster, but the sum is a real beast, because the sum up here, so you have 2 curves, right, in the real world. You first need to go down to a chart, so where the 2 curves look like this, and now you use the chart to define the sum of the curves, which might look like this. That's our sigma. But the bad thing is if I pull the sigma back, this is what we did. Well, this is the sigma down. This is x of sigma, x after sigma, right? If you pull the curve sigma up, you might get, say, this in the real world. The problem is if you had taken the same 2 initial curves, gamma and delta, and you had pushed them into another chart, there they may have looked like this, you would have gotten the sigma with respect to the other chart, the sigma y. You would pull this sigma y back to the real world, and you would get a curve through the same point or right, and would be a curve that looks maybe like this. It turns out that the tangent is independent of the choice of chart at this point, but the curves are different. So the curve, the sum of curves defined via a chart is chart dependent, but it's chart dependent in just such a way that the tangents at the point with this subtracted in this way and blah 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 so that everything fits, oh, that reproduces the same tangent vector, so it's independent of the choice of chart. The sum of curves is bad, but its derivative at the point of intersection is good.
But in fact we only use it at this point.
Yes, exactly, and therefore it's fine. That's the idea. But it shouldn't mean that you can add these curves, because otherwise you could add the trajectories of particles represented in a chart, and that would amount to adding position vectors which don't exist. So this is yet another point where if you think of position vectors and them pointing at paths and so on, you could add them. The addition is meaningless. Yet another proof that position...
Where is the problem in thinking of the sum in the same way as we did here?
You can't, because here you can provide this by scaling the parameter, but the curves, gamma and delta, they land here. And if you want to define a hypothetical addition, you can't simply add the maps, because on the target, you couldn't say you do this at lambda by taking gamma at lambda and delta at lambda, because you would have to somehow have an operation here that you want to put. But for instance, a plus doesn't exist because you don't have that. So at least in this way you can't do it. The point is you can't do it in any way. Okay? So that's why you can't add them. Again, positions do not constitute a vector space. It's always the same thing. This is yet another example of that. All right, good. Are there questions so far? Yes?
One more question about the curve sigma x we chose here.
Yes.
So the smart move is to choose it in a way that we have different arguments, lambda 0 and lambda 1, and so on, that at the end of the day we have again our 2 derivatives with the 2 different arguments which are not dependent on lambda.
Yes.
To say, okay.
Yes.
But since we have x inverse applied to the whole thing on the right hand side, aren't we chart independent from the start?
No, because in this definition you can't take out the x. You can take out the x here. X inverse after x is the identity. Yeah. But x, if the definition only went up to this point, of course you could write gamma of lambda 0 plus lambda. But then you add in the chart, and this is not a linear map, right? And so you cannot pull it apart. You can't. Okay? That's the point.
So again, a context-sensitive plus. That's the point, right?
A context... Yeah, well, it's a plus on this RD.
I know, but
yes.
you would have just cut it
Oh yeah, then it would go out in the beginning, but then you wouldn't have constructed a sum yet. Yeah, right. That's right. Okay, good. Perfect. Excellent in time. Okay, please, the blackboard. Yes. Yes. To repeat the question, yes. Thank you. So here the question was whether the x doesn't go out already in the definition. The answer is no, because the x inverse is not a linear map. Thank you. All. Yes?
You need to check all the axioms for the vector space, right?
Yes, in principle you do, but it's always the same construction. Of course you do, and you can do yourself, but it's always the same construction because we added maps whose target is R. We inherit the addition from R over there, and almost everything immediately comes from the axioms of the field R, right? So that's K plus, K times for R without zero, and the distributive law, and with them you inherit all the vector space axioms in a few steps. So it's a standard construction, but you're right, I have to show that in principle. Okay. But so anything I do not show, you have my quality guarantee it's true. Okay, so we have a notion of velocities. We have maybe this intuition, oh, they survive as directional derivatives, and because I know how they act on anything, they could act on the coordinate functions that would give deltas, and I could extract the components again. So maybe you're happy with this. But the point is, it's very useful to now go to a chart, to take the abstract notion of velocity, which will later on in physics correspond to the velocity of a particle in the real world. So that's the physical, our picture or our mathematical object representing the physical velocity of a thing, fully independent of any coordinate choice. Okay? Fully independent of coordinate choice and fully independent of a choice of length. So in order to provoke contradiction, but I won't defend it at the moment, I will defend it later. The physical dimension of speed is meters per second, say. Okay? We all agree, and that's right. What is the physical dimension of the components of a velocity vector? Say, well, it's also meters per second. It isn't, it's hertz. It's 1/2. Okay, so this is just to provoke you. You will learn and you will in the end say, oh dear, it's really true, but that we'll only do after the lecture next Wednesday. And then you will realize where the missing meter is coming from. Okay, but it's an important point, and it also stalled Einstein for many years not having understood this first. Okay, so now let's do what you're all longing for. You want to reconcile this abstract notion of velocity in the real world with components. So components of a vector with respect to a chart. And we learn much more than about the components, because if you have components of a vector, you need to know about the basis. So what is the basis of the tangent spaces, or of a tangent space? Because in this lecture, we pick a point P and we'll stay solidly within one tangent space. And only the lecture after this one will then look at all the tangent spaces together and consider vector fields and so on. So anyway, components of a vector with respect to a chart. Definition. Let Ux be a chart in the smooth manifold of the smooth underlying manifold we have here. And let gamma be a curve from R, well, from R into U, into M, but it should hit, if this is the U, the curve should hit the point P, and it better lie in the chart we're looking at. Okay? Let B, gamma, thus be the portion of a curve that lies in U. And then we can, and let's also assume gamma of 0 for simplicity hits the point P. Can all assume all of that. Now we calculate. We start with just the vector tangent to the velocity of the curve gamma in the point P. We just start with that. What is that? Well, in order to really understand it, we need to let it act on an arbitrary function. It is f after gamma derivative at the point 0. That's what it is, directional derivative. Now we insert our chart just for fun in order to get it into the game. We have this at 0. We re-bracket like this. You see it's always the same calculation. That's why one can do them. And here you have from RD to R a map. And here you have a map from R to RD, or always portions of RD. Now we do the chain rule as before, but now let's look at another aspect. I take x after gamma, the ith component, then I take the derivative at position 0, that's the inner derivative. Now I take the outer derivative, that's the derivative with respect to the ith direction, there's the summation of f after x inverse, and that's evaluated at x of gamma of 0, that's evaluated at x of p. Now, this expression and this expression will appear again and again and again. And remember, this is a function, here is a function from RD to R, and in the tutorials learned that the partial derivative, we will not write d by dx or something like this, because all you need to know to take the partial derivative is you need to know with respect to which entry do you derive. It has nothing to do with how you will, after you derived, name the entries. It's enough, it's the equivalent of in analysis, you have a function from R to R, so this is analysis, undergraduate analysis. The derivative of f is denoted f prime, and it's again a function. And you may evaluate f prime of x, or you may evaluate f prime of y. That doesn't make a difference. The derivative is called f prime. It would be very silly to say, oh, only because I give a certain prescription like this, therefore I should write the derivative as df by dx. Because the abstract notion of derivative has nothing to do whether I define this by x or define this by alpha. Right? So this bad notation we're not going to use, we say with respect to the dth derivative. Now, however, here in this expression, and now you, okay, I need many colors. Now in this expression, let's first take the expression over here, so after the multiplication sign. This expression here has many elements in it, and it's very cumbersome to write. And we write it differently. We write it del because there's a del in it. We write by del, well, there's still a del in it. This x here, now you need to be very observant. There's an x here, and there's an x here. And in order to remember that it's an x and not a y, we put an x here. Now, there is an I down here. This I has nothing to do with the x, nothing. Nevertheless, we put it up here, xi. Okay, this is just notation, that's the point. And there is an f here, that's the blue f. Great, it's the blue f. We put the blue f here. We still haven't taken care of the p. Well, we put brackets around it, and we put the little p, running out of colors, we're putting the little p down here. That's our notation for this. And you say, oh, partial derivative. No. No, because, of course, it's designed to make you look like this, because later on you can prove that this object satisfies all the rules you would like this guy to have if you don't know anything about the background, right? So this makes GR accessible to the masses. But the point is, it's very important to realize this point. The function f here is a function from m to the real numbers, or rather from u to the real numbers, because we're depending on this chart. So whenever you see the symbol, don't be deceived by its simplicity. You immediately need to translate it into this. No alternative to that. Okay. Now here we do something similar, but this is just for fun to make it look even more normal. This is the chart representative of the curve gamma with respect to x, and the ith component of it, which after I took the ith component, I derive and I evaluate at the point 0. And because we already used here some funny notation, I take the freedom to put it here as a dot with respect to the parameter. It's just for fun, so I can define this here as well. Okay, so what do we have? We have that the velocity to a curve gamma in the point P as it acts on F equals the chart representative of the curve with respect to the chart X that I chose, the ith component of it. So this is what the undergraduate idea of a position of a curve is, and you take the derivative at the point you're interested in, so a parameter value 0 because you're interested in a point P, times the, well, you may be tempted to say this is the directional derivative operator, and you let the whole thing act on the F. And that's what I wrote down very much in the beginning. You have a notion of components of a vector, you dot them into partial derivatives, and that acts on the function. Only that the function we are dealing with is not a function on the chart. The function here is a smooth function on the manifold. Okay? So, however, we have this, and it's tradition to delete these brackets to say a vector acts on whatever is behind it. It's tradition, because then it's even simpler to look at just this bit of the equation and this bit, because this is true for all f in C infinity m. So as maps, as a map, which this object is, it's equal to, if you use a chart. Under use of chart, you can understand the vector as what you would normally say are its components, and how you calculate this, you derive the components, but because it's a vector, it doesn't only have components, it also has a basis. And obviously, quite obviously, if these are called the components of the vector, which we will say, these are the components of the velocity v gamma p, then this guy here, these must be the basis elements of, well, of the space in which this guy lives. Where does it live? It lives in the tangent space. These must be the basis elements of the TPM with respect to which the components need to be understood. Right? If I talk about components of a vector, I need a basis for the vector. Now here, what we have is the so-called chart-induced basis of TPM. Choice of a chart X gives you a choice of basis in the tangent space. But of course it's fully irrelevant what chart you choose. You could have chosen a different chart, would give you a different basis in the tangent space. Okay, so now for pictures. Picture. In the real world, which might just look like this, you may have a vector here that looks like this. You may, in another tangent space, have a vector like this, another like this, and another like this, and so on. Okay, a field like that. It's good I didn't do it rotating to the right. Maybe, well. So the point is, you can map this down to a chart. Well, first of all, what you map to the chart, to the R2, is the points. You know, you have a U here, and each point goes to a point here via a chart map X, right? But now imagine that the way I do this is that if I pull this coordinate net backwards by X inverse, I would get this. Okay, this is now going bad. Okay, I need to first draw the net and then... I could have chosen polar coordinates, which means this net is mapped to this, apart from some slits and so on. And you have your vectors here attached like this. Now what you can do, you can, of course, the circle up here, the points, these points here are, of course, simply this in a polar coordinate system. Right? If you think of this x2 as the phi and of this x1 as the r, it's the generalized coordinates of classical mechanics. It looks like this. So what do you guess are the components of these vectors at the various points? Well, there will be something like this. Drawn into, if you now take the idea, okay, you have these components 0, 1, 0, 1, 0, 1 all the time, and then you draw them at the respective base point. This one here, and this one here, and so on. And then you see, yes, your vectors are associated with components, but in the chart it can look dramatically different from the world, if you wish, and depends on the chart. Clearly, if you now make a so-called Cartesian coordinate system of the same situation in the real world, so this is a bird flying in a circle, that's an objective reality, but in a polar coordinate chart it runs like this. Would you say it runs along a straight line in reality? No, it doesn't, right? But in this chart it looks like that. So you see the components of vectors heavily depend on the chart. And in principle, drawing them up here is a bad idea. You should always draw them down here. Okay, but nevertheless there is a velocity that the bird has here, and there's a velocity, but in this chart it looks like this. Okay, so that is this. Number 4 is the chart-induced basis. And I already mentioned it, so you have the definition. If Ux is a chart in the smooth atlas, then d by dx1 at the point P, d to dxd at the point P. These are all elements of TPM because they're the corresponding maps, right? And they constitute a basis of TPM. Okay, so we already saw they generate TPM because I can represent every vector in that basis. It remains to show, proof, so it's not a definition, it's a theorem, well, of the easy type. Proof, it remains to be shown that they're linearly independent. How do we do this? Well, we need to take the vectors, and I may call them vectors because they lie in the tangent vector space. We take these guys and we multiply them with lambdas and take the sum and require this be 0. And we need to be able to show that therefore all the lambdas are 0. That's linear independence. But that's simple because I simply apply the whole thing to the jth coordinate function. And in the tutorials you learned that the jth coordinate function, okay, I'm sorry, I said it constitutes a basis of TPM. It only constitutes a basis of the TPs that attach to the chart domain, right? Only in this area. We learned in the tutorials that the chart maps that go from, the coordinate maps that go from U to R, that they're differentiable with respect to the maps in this atlas, to the charts in this atlas, right? So we are allowed to apply it here because it's a function from U to R. And now comes, we would say, oh, dxj by dxi, that must be a delta ij. Well, I told you, whenever you see the symbol, you need to reconstruct what it really means. So let's do that. So let's do it up here. It's better. You can see that's better. So this means, yep.
I did not get why TPM and TPU are different.
TPU is just an area. So you have the whole world. you have the domain U. In the domain U, your chart is valid. And we use the chart map, and so you can only, intuitively speaking, this is the basis you have in the real world, but I shouldn't draw it as arrows. But this only works in the domain U, and generally, we'll come to that, next lecture, you cannot generally for any manifold, you cannot for every manifold find a global chart in the first place, but even if you can cover it by global charts, you might not be able to find a global coordinate-induced a basis field.
So basically,
Yes.
you're varying now the P within the U.
No. I said, so the statement is for any point in P. For any point in U. Right? So this is always the assumption that the chart contains the point P. I should always emphasize this. So the point P must always lie in the chart. Or rather, the chart must be a neighborhood for the point. Okay, so I apply this here. So what is the definition of this symbol? It means take the del I, compare, I think it's still down there, take the I and put it down in the del. Then take the function you're acting on, that's xj, do it after x inverse, and evaluate at x of the point P that's down here. I just did this blindly. This is just this by definition. Okay? Right, but now you see, that's very simple. This is xj after x inverse. What does that do? That goes from Rd to R and takes the tuple alpha 1 to alpha d, which is an element of R. It takes it to the alpha j, to the jth component. Right? But doing that and deriving it with respect to the ith component gives a 1 if I equals j. And so there's the sum here, and this is the delta symbol I introduced, and this is lambda j. But we start with the assumption that this object is already 0, so applying this to this yields you that all the j are 0. That means these guys are really linearly independent. So indeed, this constitutes a basis. And the corollary of that is that the dimension of TPM is of course D, because you have D basis vectors, but D ultimately came from the fact that you have D coordinate maps. So the dimension, the vector space dimension is D, and the manifold dimension, which is a very different concept, is also D. So the tangent space at each point has the dimension of the manifold. Well, that's quite intuitive, but one is a vector space dimension and the other one is a topological manifold dimension. Yes?
But shouldn't it be then TPU all over the place in the right black box?
This is right, but it remains right if I do this. Okay, but you're right. Constitute a basis of TPU is certainly right. TPM would be wrong because not for every point P and M. Okay, that's it. Yeah. Yes, but here I would argue I did this now for one point, but there I have a neighborhood. I can do it for another point, and because it covers, I know it everywhere. Thank you. That completes the proof. Yes. Okay. So time is almost up, 5 more minutes. I asked to bear with me for maybe 15 minutes, and then I don't need to rush through it. Is that all right? And then maybe we shift again, because then we get this important topic covered. Yes? Okay. So, next topic is change of vector components under a change of chart. Now, in the older literature on differential geometry, statements of the following type are to be found. Tensors transform under a change of coordinate systems as follows. A vector transforms as follows. Well, most precisely, it must say vector components transform as follows, because the vector is an abstract object. It's the velocity of the bird at that point of time. No change in your thinking about the coordinate system will change the velocity. The velocity is the velocity in the real world. But if you think of the components of the velocity in a particular chart and you change to another chart for the same velocity, of course the components will change. There's something different. So therefore it is to be said change of vector components under a change of chart, not change of vector. So I emphasize vector or tangent vector does not change under change of chart, simply because it's defined independently of chart. How would it change under a change of chart? So let's see how that works. I should have maybe added some terminology here. I'm sorry. Terminology. If X is an element of TPM, then you know two things. The first thing you know is that there always exists a curve gamma such that, so gamma curve, such that X is the velocity of some curve to that point, through that point P, if X lies in TPM. So I pick an arbitrary element of X from TPM, and I will in the future not always make explicit the curve it comes from. In fact, it doesn't come from the curve because these two curves give the same vector, right? So therefore we'll talk about this abstractly, and that's the first thing. We sometimes need, and it always arises like that by definition of TPM. And the second thing you know is because it's a vector space, you can always find, so there exist x1 to xd, which are all numbers in the real numbers, such that x can be written as a linear combination xi d by dxi p if you have a chart. But you can also, quite independently of chart-induced coordinates, you could choose, because it's a vector space, just any basis in it. It wouldn't then come from a chart, but it would nevertheless be a basis, and you expand in components. And the xi are called the components of this with respect to the chosen basis, and the basis may come, or you may induce it from a chart, or use it at a point. You define it just like this, because you say, I like these three vectors to be the basis. You can do this, okay? You don't need to come from a chart, but if you have chosen a chart anyway, why not? Because you already committed the sin, right? So then you better enjoy it. Good. So change of vector components. So now, in order to consider the change of chart, let's do the following. Let u, x, and y, vy be charts, but let them be overlapping charts. And take a point P from their intersection. Okay. Now, let x be an element in the tangent space of this intersection. Then we know that we can write, with respect to the chart ux, using that, we can write this as xi components d by dxi p, because that's the basis. And in order to indicate that these are the components with respect to the basis from this chart, we mark the components by a little x down here. But now, of course, fully independently, you can choose the chart Vy, because the point P is in both, is in the overlap region. and you can choose different, or you must generically use different components with respect to the different bases. All right? And the question is, how are these components related to those components? And you know there is a relation because the abstract object in the middle is invariant under this. And now we look how this goes. Well, let's simply start with this object. So in order to study change of components formula, or to derive it, consider the following. We take d by dxi at the point P, and we try to reformulate it as this guy. We know it's a map, so we best understand it if we apply it to what it acts on, namely a function. And what now? Well, you see this symbol, you know it looks very deceptively simple, but you have to translate it. You let the I jump here, you take the f here, you take after the x that's here as the full map inverse, and you evaluate at the point x of p. You need to be able to do this back and forth in your sleep. That's what the weekend is good for. So you have this, and now of course we want to consider a change of chart. So if we want to relate this x to this y, we better have it somewhere, so we insert it as an identity at this point. Right? Nothing happened. Right? We just inserted the identity, we use the associativity of the composition, and we re-bracket. Now things are simpler again, because this is from RD to R, some portion of RD to R, and this is from RD to RD, and by the way, it's an old acquaintance, it's a chart transition map. However, it comes here derived. So we execute the multidimensional chain rule. The inner derivative is del I acting on y after x inverse, but this lands in RD, so it has a jth component. And it's evaluated at x of p. Times, now comes the outer derivative. It's this guy, which is derived according to the multidimensional chain rule, like this, and summed over these results, of f after y inverse, and after you calculate this, you evaluate at this, at y after x inverse of x of p is y of p. You evaluate at y of p. Okay? And now you stare at this for a little moment, and you say, oh, that's nice, because the ith derivative of the jth component of this j comes because the y lands in RD. So you could have also taken the coordinate function instead of the full coordinate, the full chart map, and then the jth component is of course the jth coordinate function. So, but this is a coordinate function, so you have del I of a function after x inverse x of p. Oh, we know this guy. This is del y, it's a jth component with respect to the dxi down p. For this object, we can also use our symbol. And now you look at this and you say, oh, f after y inverse, j, da, da, da. Ah, this is also our symbol. This is df, but now with a y instead of an x. J. So this is a j, and this is an I, at the point P, because that's what the symbol is. Ah, and where is this guy here? Well, that's a real number. And so you have here a sum that goes like this over that. And so here you had this symbol, here you have the f. You can consider the whole as an operator that acts on this. Okay? And so what did we find? We found that this guy here, because this is true for all f, didn't make any assumptions on the f, is the same as this guy here. Okay? So let's insert this into here. Therefore, insertion into that yields you, how do we do that? Okay, x ith component, and for future use, let's make this a jth component from the beginning. I just renamed the summing index. xi with respect to x of the d by dxi, but the d by dxi I reformulated like this. dyj by dxi at the point P times d by dyj at the point P equals, and then I just copy the left-hand side, is xj with respect to the y system, d by dyj at the point P. Aha, but because these are a basis, I can take this to the other side. I factor out the basis. I have numbers times the basis is 0. I know the numbers are 0. Or written like this is the jth component in the y system is the constructed from the ith component in the x system by multiplying with yj by dxi at the point P, and the contraction is over this. And this is the formula you find in books. It says if the xi are the components of the vector in the x, in the basis with respect to the x chart, then the very same vector, the same abstract object, the same physical vector, if you wish, as physicists, has in the y chart components that you get by calculating these numbers at the point P. Now, your change of coordinates can be wildly nonlinear on your manifold, wildly nonlinear. But now you go to one point and you look at the components of a vector with respect to the original chart, and because you evaluate this wildly nonlinear dependence of y on x and stuff like this, you evaluate this at this one point, you just get a scheme of numbers, one might say a matrix, which one might say matrix multiply into this column vector, right? But we don't want to use the terminology. You construct the sum. This is at a point for a given change of chart from one chart to the other chart. At that point, it uses a constant matrix, which is the matrix that takes the components of the vector in one system to the components of them in another system. So we have a vector space and it's acted on at each point by a linear map, by a constant linear map, which only depends on the change of chart, although the global chart transformation is wildly nonlinear. Now what you do in special relativity, let me tell you, you talk about Minkowski vector space. So doesn't that fly in the face of everything I said? Because Minkowski vector space as the points in space-time is a vector space, right? The x mu's and stuff like this. Yes, it flies in the face of everything, and you shouldn't say that. Minkowski space, the position, the space-time points in special relativity, everything is flat, is not a vector space either. Now, you say, well, but the formulas work. Yes, they work because you artificially restrict yourself to changing from one coordinate system to another one by linear transformations, which you further restrict to be Lorentz transformations. And this sounds like a good idea. Well, it's a good idea for the individual velocity vectors. Velocities transform under Lorentz transformations in each point of the flat tangent space by a linear map. Now, but that doesn't mean that I mix the points on the space only by linear maps. I want to be able to do special relativity in polar coordinates if I wish so. You can still do it. You can change from Cartesian coordinates to polar coordinates, and in the velocity tangent spaces, it will induce indeed linear maps. And if you say observer velocities should stay observer velocities, you can think about what you have to require. But not in position space. It's an over-structuralization to equip the position space of special relativity with a vector space structure, because you then transform also position vectors with Lorentz transformations, which is, why do you restrict yourself like this? In the tangent spaces, it makes a lot of sense. Okay, so that's the statement here. Okay, so we have this. So there is one more thing I would like to mention, and that's cotangent spaces. And now it pays off what we did yesterday. So at a point, you have a tangent space TPM. But this tangent space is just a vector space with the operations we defined. So of course, it's quite trivial to consider the tangent space, which is a vector space, and to consider its dual. So you consider all the linear maps from TPM into the real numbers. So we're still at this point, but now we look at the dual space. It's a very simple and straightforward construction. Now the point is simple and straightforward, but are there any objects we're interested in that lie in it? Yes, there are. Imagine you have on your manifold a smooth function, say a temperature distribution. Then you can define the following object, d, df at the point P. So we take a point P and you define this as the map that takes a tangent vector at P and maps it linearly to the real numbers by virtue of sending the vector to df at the point P of the vector, and this is defined as simply the action of the tangent vector at that point to the function. So you say, okay, this we knew how to write down before, this directional derivative. Why on earth do you want to introduce this complicated notation? Well, we wrote this action x on f this way as a map from the x space, the space where the x's are, linear map to R. That means that this df at P is an element of the cotangent space. And what is this? Well, this is the gradient of f. So df sub P is called the gradient of f at the point P. And you do not need any charts to define the gradient. Now we can calculate the components of the gradient. And you remember how you get the components of a tensor. It's a 0-1 tensor, right? It's a 0-1 tensor over TPM, right? In our terminology from last time, 0-1 tensor over the underlying vector space, which happens to be TPM in this construction. So the gradient is a 0-1 tensor or a co-vector, and calculate the components. How do you get the components of a 0-1 tensor? Well, you write down the tensor abstractly, and if it's a 0-1 tensor, it has one index down. How are the components defined? Well, you take the abstract tensor and you plug in the basis with respect to which you wish to get the components. Well, a 0-1 tensor eats one copy of the vector space, an element of a copy of the vector space, and say we want to do this components of the gradient with respect to the chart induced basis for the chart ux. Why not? So we plug this in. So what is this? This is the jth basis vector, and that was this object. Let's calculate this. Well, this applied to this vector is actually the vector applied to the f. D by dxj of the fp. There we got it. Now it looks deceptively like what you would do. You say you take the partial derivative in the j direction. You know that you need to translate the symbol into del j f after x inverse and evaluate at the point x of p. And this you can calculate by undergraduate analysis. And because you evaluate at the point, you get a number for each j. These are the components of the gradient. And the gradient components are covectors. The gradient of a field, of a function, is not a vector. The gradient of a function is a covector. There's nothing to be done about it. It's a covector. It, for instance, under a change of chart, these components transform differently than the components that have an index up. So the final thing I write down is the change of components. I won't prove it because you believe it works exactly like for the vectors. Change of components of a covector under a change of chart. And again, the same applies. It's a change of components. The covector remains the covector. Maybe I emphasize this. So if this is an element of TPM star, and you see the star is here, and it's tradition to write it there. So don't be confused. It means nothing different. So if this omega is in TPM star, it can be written, I forgot something important. I'm sorry. Let me put this here. Theorem. I want to give you a coordinate, a chart-induced basis for the cotangent space. Theorem. Consider a chart UX. That means you have chart maps xi from the chart domain to the real numbers, right? You have these coordinate maps. The claim is, well, first of all, they're all smooth functions with respect to the chart that's the atlas that's underlying. The claim is that if you take the first such function, you of course can calculate the d of the function. So you take the function and then you apply the d and you evaluate at p according to this definition. And then you take the next coordinate function, this is the function, then you apply the d, you evaluate at the point p, and so on up to the dth coordinate function, you evaluate at the point p. And the claim is this is a basis of Tp star m. And in fact, it's the dual basis. In fact, this is the dual basis of the dual space. What do we mean by the dual basis in the dual space? In the dual space, we could choose a basis that's totally independent of this basis we chose in the tangent space. But it turns out if we construct it as the gradients of the coordinate maps, you can calculate. You take the gradient of the eighth coordinate map at the point P and you apply it to the bth basis element of the tangent space, and you calculate this, you get dxa by dxb p, and by writing it in undergraduate analysis notions, you get indeed delta AB. So in fact, this is not just a basis of the dual space, it's the dual basis of the dual space if in the original space you chose the chart-induced basis. Somebody had a question? Okay, sorry, I wanted to say this first. So we have a chart-induced basis there too, and it's given as the gradient of the coordinate maps. Now, how do the components of a covector, which is an abstract object with physical reality, we would say as a physicist, you can expand in terms of the dxi's at a point P, if this is an element in the cotangent space, and we label the components like this, of course, it's a covector, and with respect to the x chart, and here with respect to the y chart, or a y chart, we may label them like this and expand in the y dual basis. Now you go through the same motions as we did before for the vector. You express this in terms of the other, you use again the multidimensional chain rule, and what you arrive at is the fact that in the y system, the ith component is given as the ith component in the x system, d, and now we need to see where the y and the x is, and the rule to remember is this index is down, but I need an x and a y, they have both an index up, so this index down comes from an index up if the object is under the line, so the I must come from here, the I must come from here, And this J must relate to this one because up, down, right? And then the J is an xj, has an x with a J with respect to an x. I mean, this is a mnemonic rule, right? And here you have a Y. So you need to find some way to remember where which object goes. And if you compare this to the transformation of vector components, you will see this is the matrix with x up and y down, whereas the vector components go with y up and x down. Okay? If the result is the y result. And then you can show, and that will be on the problem sheet today, that these two matrices are inverses of each other. So really, the components of a covector under a change of chart are transformed the other way linearly than the components of a vector under the same change of chart. And now imagine what happens if you call the gradient vector, and you believe your terminology, you're in direct contradiction to the chain rule. Right? You don't need to know anything about differential geometry. You write down the gradient like this, you define the components like this, you do the chain rule, which is undergraduate analysis, and you will find the wrong transformation behavior, or at least wrong compared to the assumption that it transforms like a vector. Right? It's not deep, it's not a special new mathematics that makes the gradient a covector. It's the chain rule of standard analysis that makes the gradient a covector and not a vector. It's a very important point to keep in mind. And in tutorials, in the first half of tutorials this afternoon, this has been further investigated. Questions? Okay, then we reconvene, I suggest, at 10 past. Thank you.